Thanks for the introduction, and thanks everyone for coming. And I would like to thank the Department of Structural Engineering for inviting me here. As you can see, the title of my presentation is Mechanics and Manufacturing of Composites for Durability and Damage Tolerance. So here's the outline of my talk. I'll start with a brief introduction to composites and few relevant applications, and I will talk about research highlights of ongoing research activities within my group, and I'll talk a little bit in detail about two research topics. Can you all hear me well at the back? Okay, great. And I will conclude with some plans for future work. So, textbook definition, what are composite materials? Well, composite materials are hybrid material systems which consist of two or more monolithic constituent materials that retain their individual identities but result in a material with improved physical and mechanical properties compared to the properties of their individual constituents. Typically, composites have a reinforcing material which is of high strength and a matrix material that binds the reinforcements together. And here are a few examples of commonly used composite materials in mechanical and civil systems. Here's a carbon fiber reinforced polymer composite where the reinforcing material is a carbon fiber and it's bound together by polymer matrix. And this is a honeycomb structure where there's a honeycomb structure that is sandwiched between sheets of polymer matrix composites, and these are excellent in flexural behavior. And very often for high temperature applications, we use a material system called ceramic matrix composites. And in this particular case here, is carbon fiber reinforced in silicon carbide matrix. And some of you may have your background in civil engineering. We know that concrete is one of the most commonly used composite in civil infrastructure. And we know that it's very good in compression, but kind of weak in tension. So they are reinforced further with textiles or steel bars or fibers. So we improve both the compressive and tensile behavior of these composites. Well, such composites have a large range of applications from aircrafts, automobiles, bridges, pavements, and wind turbine blades. And very often, due to extreme conditions that act on these structures, it could be natural or man-made hazards, can cause damage and failure of these structures. For example, fatigue load or bird impact on an aircraft, a car crash, due to some moisture absorption or along with fatigue load acting on the structure of bypassing of vehicles can cause damage and failure in beams and columns. And in some cold regions, due to thawing and freezing effects can also cause damage of pavements. And some very extreme conditions like lightning strike can also fail structures like wind turbine blades. Now, it's very important to understand and be able to predict such damage and failure behavior in these complex systems to assist in the design of durable and damage-tolerant structures. Having said that, my group at UTEP, which I like to call Manufacturing and Mechanics Lab, we use concepts from mechanics, manufacturing, and materials to design improved materials for resisting any dynamic or damage that could be imparted during extreme conditions. Now, I would like to highlight few research activities that are ongoing within my research group, and I like to divide that into different conditions that can act on these composites. Few are manufacturing defects, high thermal shock, cryogenic exposure, Arctic, and impact damage. These are some of the extreme conditions that can occur in composite materials. So this work is in the manufacturing process for textile composites. And here we seek to develop a computational tool that can predict the behavior of the final composite after a manufacturing process. In this particular case, it's a vacuum-assisted resin transfer molding process. And our goal is to predict the final response of these materials and capture the influence of different manufacturing-induced parameters on the damage initiation and evolution in these materials. Impact damage. Well, within this work, our focus is on improving the damage resistance and durability of layered composites. And we know that in layered materials, the interlaminar regions, or the regions between layers, are highly susceptible to damage, in particular delamination or separation of these layers. And our goal is to improve the interlaminar fracture toughness of these materials when subject to face impact or edgewise compression, because that lead to delamination type failure typically. And we have used a novel material called zinc oxide nanowires, and we have observed significant improvement in the interlaminar fracture toughness so far. So this is another is in high thermal shock. Now, as I mentioned earlier, ceramic matrix composites are used for high temperature applications, and our goal in this work is to develop a multiphysics problem or multiphysics computational framework that can be used to predict the response of these ceramic matrix composite, in short CMCs, in particular carbon-carbon composites in oxidizing environment. So we want to capture how the oxidizing environment, thermal shock in these extreme conditions can cause reduction in the initial stiffness and the strength of these particular materials. And we have so far good correlation up to about 700 degrees Celsius of peak temperature that is imparted, and we do not have a very good correlation beyond that, and we are currently working on improving that in particular. So this is a very recent work that we started with the Office of Naval Research, where our focus is to investigate the influence of Arctic seawater conditions on materials that are currently being used for naval applications like foam sandwich composites. And our goal is to improve the life cycle and structural integrity of these structures when exposed to such harsh environment. And we are focusing on the constituents like the foam and the face sheet separately, and all of them together. And we are also looking at some alternative or alternate foam materials for these sandwich composites. And the last that I want to touch upon is in textile composites for cryogenic fuel tanks. NASA has been trying for a couple of years now to reduce the overall weight of these cryogenic fuel tanks. And for the first time, we have incorporated or studied the usability of textile composites for such systems. And there is a huge thermal gradient that exists from the interior and the exterior of the wall. And we are focusing on designing the wall of these fuel tanks to minimize the effect of such high thermal gradient that can occur due to cryogenic fuel tank within these structures. And for the same, we're developing a computational framework which can assist in the design of such components. So far I've talked about just a glimpse of different research activities, but in particular, I want to expand upon two topics today. One is the manufacturing defects and the impact damage. All right, so this work is in textile composite manufacturing. Now, textile composites are used predominantly in automotive, energy, naval applications, and so on. And they are relatively cost effective to manufacture, and they have relatively higher fracture toughness. A very good aspect of these materials is the drapability. That is, it can conform to the shape of a component well, thereby minimizing any damage that could occur in the reinforcing fabric themselves. Having said that, these materials are very complex. They have different length scales ranging from microscale to macroscale, and the fibers that are reinforcing in these composites are of the order of few micrometers. So this is a microscale structure, which bundles of these fibers are then woven or braided together to get sheets of fabric, just like your cloth, shown here. And they're stacked on top of each other, infiltrated with resin, solidified to achieve a macroscale panel of the order of few meters, which are further used in components. Now, so the bundles of fibers called tows are of the order of few millimeters, which constitute the mesoscale in our structure. Now, damage can occur at very small length scales in the form of micro damage or micro cracks. And accumulation of such damaged regions can cause large cracks at the macro scale. So it's very critical to bridge these length scales to capture the effect of damage that occurs at the small scale all the way to the large scale. All right. So as I mentioned, we are focusing mainly on the VARTM process, which is the vacuum-assisted resin transfer molding process. And this is a process that is most commonly used for manufacturing large panels of textile composites. And I'll come back to that later in detail. But very often, right after manufacturing a particular composite, we observe damaged regions in the form of large cracks, delamination, or micro cracks within the material. Now, that is prior to applying any external load. So these defects are caused just during the manufacturing process. To support that a little bit more, a work by Song et al. Looked at the shear stress, shear strain behavior of a bulk cured resin, which is used in these composites, and they observed that their behavior was superior to the in situ cured resin. What in situ means is the curing of the polymer in the presence of fibers during the manufacturing process. And when this was used to predict the compressive response of textile composites, it was observed that there's a large reduction in the peak stress value. So what this means is the quality of the material fabricated, what we expect is not the same that we achieve after the manufacturing process. It's something completely different. A little bit more in-depth study showed that when we use two systems with the same reinforcing material, for example, carbon fiber, and the same architecture of fiber, but and also identical manufacturing process, but two different resins, Hetron and Epon, we observe that the damage that is caused within the material are very different. There is cracks that showed up in the Hetron case, and the material was very good in the Epon case. These two resins behave identical when measured in bulk, but in the presence of these reinforcements, they showed completely different behavior. So that was mainly attributed to the relative difference in the cure shrinkage that could occur during the curing process. So to summarize, we need to account for manufacturing-induced damage due to different reasons. It could be the type of resin that's used, it could be the manufacturing steps, the temperature, the pressure that is applied during the manufacturing process. So our goal is to account, or at least be able to predict the influence of different manufacturing parameters at different length scales from micro to macro scale. So this is a slide that I showed earlier. So again, our goal is to develop a computational model. And this is a schematic of the VARTM process where we start with dry fabric, that is layers of reinforcing material stacked between two mold plates, and it's wrapped or covered in a vacuum bag as shown here with an inlet and an outlet pipe. The outlet is connected to a vacuum pump, and the inlet is connected to a mixture of resin and hardener, and the vacuum assists the transfer of resin through the system. And then it's cured and we get the laminate. Just to put it in perspective, this is a canoe structure of a couple of meters, 4 meters by 2 meters approximately. And these are the key steps that are involved in the manufacturing. So we start with the mold, which the shape that we desire, and we apply gel coat so that we can separate the laminate eventually after curing. And we place dry fabric. In this case, it is glass fiber reinforcements, and we lay a couple of sheets depending on the thickness that is of interest to us, and then we apply a seal tape, and then we place this resin transfer fitting which assists the transfer of resin, and we enclose the whole system with a vacuum bag with a couple of ports around the structure, and they're connected through pipes to a vacuum pump, and that assists the transfer of resin. The dark region that you see here is the amount of resin, or the amount of area with impregnated resin. And after the complete infiltration the resin has completely infiltrated, it's cured, and the canoe is separated, and this is the structure. Now, a couple of things here. The curing of polymers, resin, is generally very exothermic. That means it generates a lot of heat during the curing process, and depending on the shape of the structure that we are interested in, there could be excess stress concentrations that could occur, which could damage the material during the process itself. So it's very important to account for the heat generated in the presence of pressure and the shape of the component itself. All right. Moreover, if we look at the evolution of temperature in a canoe structure, it typically looks something like that, where we start with a room temperature curing, but eventually there is a large increase in temperature. This is just to corroborate the fact that the exothermic reaction generates a lot of heat during curing process, and that could deform the structure excessively or can cause high stress concentrations, as you can see there. All right. So we have established that the whole manufacturing process, which involves curing, is a multiphysics problem. So we now split the process into multiple steps. Step 1 is the infusion of resin assisted by compaction. Next is the curing of matrix. It could occur either at room temperature, or it can be expedited by applying a cure temperature cycle. And once the curing is complete, we determine the mechanical response to understand the effect of the curing process. So in our computational framework so far, we have assumed that the transfer of resin is uniform. I'm working with some people in the fluid mechanics part who can assist us with the interaction with the fluid infusion with the, through the preforms. But our focus is mainly on the effect of curing of matrix on the damage evolution. So these are the steps. As I mentioned, the process is highly exothermic, so we need to determine the temperature distribution in the model that we consider, and followed by stress evolution. As curing progresses, the material solidifies, so there is stress evolution. And if the stress at any material point exceeds the strength of the material or the critical stress of the material, it can degrade. So we need to incorporate any degradation that could occur during the curing process, and finally determine the response to applied load. So here, first step is evolution of temperature and degree of cure. So here we start with solving numerically a heat transfer problem with some aspects of curing feeding into the heat problem. I'll explain this in a little bit in detail later. Once we understand, or once we determine the temperature, and phi is the degree of cure, how much solidifications occurred, we take these two as inputs in the evolution of stresses, which is given here. Again, I'll come back to this later. This is just to show what are the inputs at different stages of this multiphysics problem. So the stresses, when the stress evolution is assisted with curing, and when it reaches a critical value, we need to damage the material, and we include a crack band model to account for the damage. As shown here. Again, I'll talk about this a little bit in detail later. So this is the full framework of our multiphysics analysis to determine the influence of curing. So we start with a one-way coupled nonlinear partial differential equation, a heat transfer problem, and this part is the heat generation. And as you can see, the heat generation is related to the rate of curing of the material, and that is defined by an Arrhenius type equation, which is measured experimentally. Now, that to explain how the curing occurs, we start with a mixture of hardener and resin, and at this stage, it's in the liquid form. With time, crosslinks form, and they can carry a shear load as crosslinks build. And finally, the cured material is a solid material when all the crosslinks have formed in the polymer. And that degree of cure is measured sequentially during the curing process as the heat released to the total heat of reaction. And these measurements are made in digital scanning calorimetry, and that and by fitting those responses, we can get the Arrhenius type equation that gives us the extent of heat generated in our thermal problem. So we need to consider the temperature distribution, the chemical evolution that occurs, and the evolution of mechanical properties that is related to the extent of cure that has occurred. All right. So we need to now relate the thermochemical evolution to the mechanical evolution, which is the build-up of stresses. So we followed a network formation theory for this. That is, if we have only 3 networks in a liquid, it's in the liquid form, as curing occurs at some time t1, one network forms. So that is a solid now. So it is accompanied by shrinkage that occurs. And at some time t2, another network forms, further shrinkage occurs, and at time t3, all the networks have formed. Now, of course, in a polymer, it's not just one network that forms. There can be a zillion networks that form during the curing process. So it has to be a continuous process, and we account for that by integrating the rate of cure and accounting for the development of bulk modulus and shear modulus with the degree of cure. And this part is the cured networks or solidified networks, and it's related to the effective strains, and that strain accounts for any cure shrinkage strain that could occur and any strain due to thermal expansion. And the second part is contribution from the uncured networks, and these are in the liquid form. So the percentage, or 1 minus phi, is the remaining uncured network, and the contribution is only by bulk, in the form of bulk. There's no shear contribution from liquid. So now, so far we have determined, based on our inputs about the temperature distribution and the degree of cure, the evolution of stresses. Now, if that stress exceeds a critical value, we need to fail the material or damage initiation occurs. But we know that if there is a softening response in our input for in FEA, we face something called pathological mesh dependency. Now, people who have taken FEA know that when we refine the mesh, we need to achieve convergence of solution. But when we have a negative slope in our input behavior, the convergence does not occur. And we did a uniaxial study with one element of length L having that negative slope, and the other region having a regular linear elastic behavior. And for one element, that is the response post-peak. And as we increase the number of elements, the response changed. And eventually, it traversed the loading curve itself when the element was very small. Now, that means that even after failure is initiated, there is no energy dissipated, which is incorrect, right? So we use the crack band model, where we convert a material behavior where sigma c is the critical strength and the fracture toughness of the material is converted to a traction strain law. These are measurable quantities. For polymer matrix, we can determine these two properties. We convert them to traction strain law and use that in conjunction with the linear elastic behavior, which means as soon as we hit this critical strain in our material, we start degrading the material, and that which is basically decreasing the stiffness of the material. And that is now, because we have accounted for that characteristic length within the material, within the finite element framework, which depends on the fracture process zone, has now gotten rid of our mesh dependency, the pathological mesh dependency. This was first proposed by Bazant, and details of how that length is defined can be found in this paper. So we take this idea of crack band model to degrade our material once a critical stress is reached within our model. So going back to our curing process, as curing progresses, the elastic modulus increases, for example, that way. Now, it now only depends on the extent of cure. But based on the extent of strain that is accumulated, we need to degrade the material. So we convert a line curve into a surface plot, which now considers both the extent of cure as well as the separation that had occurred in the material. And this separation is related to the strain using the traction separation law. So by incorporating this law, we can predict the damage that occurs in the material due to any point that reaches that critical stress in the material. All right, so we conducted studies at 2 different length scales, one at the microscale and the other at the mesoscale parallelly, where the microscale is just packing of fibers in a system, and that is transferred to a meso model, and the meso model constitutes the macro model. So to study the influence of temperature curing cycle, we have considered a representative unit cell with temperature acting all around, and that follows a cure cycle as shown here. And after curing, the system is applied, a tensile load is applied to the system to determine the load displacement response, accounting for damage that could occur during the manufacturing process. So we considered 4 different packing with identical volume fractions. The volume fractions in each one of them is the same, but based on the type of packing, the pattern of damage shown in red regions changed from packing to packing. And in composites, there is a large variation of packing within our toes in a textile composite. And this is right after curing. Then we apply a tensile load, and we notice that the final failed regions are the regions that connected the initial damaged spots due to the manufacturing process. So from here, we do see a huge correlation between the extent of damage or the pattern of damage and the failure pattern thereafter. So here's a small video. So we start with the cured material with damaged regions, and as we apply tensile load, those damaged regions connect to provide us with 2-piece failure of the material. So the load displacement plots look something like this, and we notice that there's a huge variation in the peak load as well as this initial slope of these materials. So just based on packing, we notice that there is a large variation in the behavior of these materials. And this, now we're working on incorporating this at the mesoscale to account for such variation stochastically at the higher level. Now, parallelly, we did some parametric studies at the mesoscale where we have homogenized toes in matrix, and this model is order a few millimeters with the same reinforcing material and the matrix. And the 2 parameters were, how does the curing temperature affect the extent of damage in our material? And the other is, how does an excess compaction pressure affect the damage as well? So the first study was considering 2 cycles with hold temperatures, these horizontal regions of 350 Kelvin and 375 Kelvin for 4 different critical strengths of the epoxy that exists. And we noticed that for cycle 1, as the strength of the material increases, the extent of damage reduces, which is shown in red regions. The same behavior was observed for cycle 2, but between cycle 1 and cycle 2, we noticed that the damage regions increases for cycle 2. But which is intuitive. We increase the temperature, we expect higher stresses, so damage could occur, higher damage could occur. But when we looked at the time required to achieve complete curing, we noticed that there is a huge reduction in the time required for complete curing. Now, so that's a trade-off. We know that some damaged regions may improve, but the time required for curing can reduce. Another study was the influence of extra compaction that can be applied. So we looked at 4 different compaction pressures and for 2 different material strengths. And we noticed again that as we increase the compaction, the extent of damage increases for both of them. But the decrease in curing time was not significant. So from such a study, we can optimize, we can say that increasing the temperature for this system has a better influence as compared to increasing the compaction because increasing temperature reduces the curing time drastically while imparting only little damage in excess to the first cycle. And again, we conducted tensile studies of the same, and we noticed that the peak loads for compaction without any externally applied compaction showed better behavior than the one where we applied. And this is how the peak loads reduced. And this plateau loads are because we are not accounting for any damage within the toes so far. It's only in the matrix around the toe regions. So far, we have completed our work at this scale, and we are incorporating the extent of damage into our mesoscale model. And by determining the response of the material at this scale, we would finally determine the variation of mechanical properties at different regions of a large structure. So that's our goal, and we are working towards that now. And of course, we want to do some actual compression tests using compression press with heated platens to understand the influence of compaction and temperature in real systems. All right, so that's the work on damage prediction at the small scale. I have a couple of minutes, right? Okay. So the second, this will be short. So this is a work on impact damage. And okay. So as I mentioned earlier, we are interested in improving the interlaminar fracture toughness and to improve the damage resistance and tolerance. Well, earlier researchers have studied different methods. So the goal here is to improve the through thickness response of a laminate, right? Because we want to reduce the effect of impact damage or edgewise compression. So some methods are Z-pinning, stitching, 3D weaving. These, the reinforcement in the third direction, in the thickness direction, do pass through all the layers of our material. So it did increase the through thickness response significantly, but it also reduced the in-plane response drastically because it caused failure of fibers, change in volume fraction during weaving, and crimping of fibers. So that caused extra damage in the in-plane behavior. So these were not very successful in improving the overall behavior of the structure. Now, carbon nanotubes have been synthesized for the interfaces. These CNTs are inherently very strong, but the process occurs at a very large temperature of greater than 600 degrees Celsius, which damaged the reinforcing material themselves. So they were not good for improving the interlaminar response. So we looked into a new approach using zinc oxide nanowires. The synthesis occurs at relatively low temperatures, about 100 to 150 degrees Celsius in a solution-based method. And we did, as I mentioned earlier, we did get good results for improvement in through thickness response by using that. So this is almost an experimental work where we first synthesized these zinc oxide nanowires on carbon fabric, dry fabric, and we used the famous VARTM process to manufacture the laminate. And because we are interested in the interlaminar behavior, we conducted DCB, double cantilever beam, and end-notch flexure tests to determine the fracture toughness of the interfaces. And because we are interested in only fracture toughness along these interfaces, we synthesized these zinc oxide nanowires only at those interfaces. And after testing, we did a fractographic analysis to understand how the new surfaces behaved. And we noticed that the samples without zinc oxide nanowires, which I like to call pristine samples, showed a very smooth failure pattern on the surface, but the ones with zinc oxide nanowires showed a more jagged behavior, which means there was higher resistance to the formation of new surfaces in the case of zinc oxide nanowire reinforcement. And that was supported by our test results. So for the DCB, we used a loading-unloading type of test, and we noticed that the load values dropped significantly for the pristine samples, but for the ones with zinc oxide nanowires, the drop was very insignificant in mode 1. For mode 2, the peak loads were comparable, but the post-peak behavior were quite different. In the case of pristine samples, the drop was sudden, but with zinc oxide nanowires, they were more gradual, which showed an increase in the fracture toughness values. And we used the ASTM standards and measured the fracture toughness values, and we noticed that there is about 73% increase in mode 1 and about 28% in mode 2 response. So with this at hand, we wanted to see, can these be used to mitigate impact damage, especially low energy impact like tool drop on the structure. And it's very important, especially around the cutouts, to improve that interlaminar behavior, because that can cause high stresses at those regions. So we did some tests using a drop tower for low energy impact. Now these low energy impacts are very important because they cause barely visible damage. That means on the surface you see very small dents, but it damages the interior of the material significantly. So, and which adversely affects the residual strength of these components. So it's very important to study the effect of low velocity impact on structures. Before we could just reinforce all the interfaces in our laminate, we first did a small computational analysis where we created these individual reinforcing layers, about 16 layers, with green regions of interfaces in our model. And we actually simulated the impact test. And this is how it looks like. There is a striker on a plate which is clamped in a circular manner. And so this is how the impact test looks like. This is the front face of impact, and that's the back face. And when the striker is at maximum contact, we determine the stresses that exist at these interlaminar regions. And we noticed that 4 regions had very high stresses compared to the other regions. The surface right under the top sheet, which is this is not layer, this is interlaminar, region 1, 13, 14, and 15. So the impacted first interface and the back 3 interfaces. So we chose to reinforce only these interfaces in our laminate. We did that, fabricated the laminate, and determined the response to impact. Well, the peak force did not differ much from for different energies imparted, from 2 joules to 30 joules. But we were more interested in the extent of damage, which is a measure of the absorbed energy during impact. So we defined a degree of damage as a ratio of the absorbed energy to the impacted energy from our energy time curve. And we measured, we got this as an output, and we determined the degree of damage for the same amount of impacted energy for all these cases. And we noticed that for impact energy from 10 to 30 joules, we achieved about 10 to 15% reduction in the degree of damage. This is not satisfactory yet, but we are working on studying the influence of the size of nanowires and the manufacturing process to improve the response or decrease the extent of damage. And for these low energies, because the striker just rebounded back, there is no damage associated for those low energy impacts. So our goal is to use these nanowire reinforcements for Arctic exposure as a part of our study with the Navy, and also perform simulations to understand the influence of the nanowires at the interfaces. Well, I don't work on such small scales of few nanometers, but that's something that I'm looking to collaborate with people from material science who could assist me with that. So with that, I would like to talk a little bit about future research directions that I would like to pursue, which are a couple of these, but I would like to just expand on 3 of them today. This is basically an ongoing future work combination where we are looking at using additive manufacturing to reinforce the interfaces in these laminates. Again, the whole idea is around cutouts. The edges have something called edge effects that, because of change in properties of different layers of the materials, can cause excessive stresses here that can cause delamination. So we are developing a quasi-2D formulation to understand the free edge effects, which can be used to spatially vary the reinforcements by the assistance of additive manufacturing process to reinforce those edges, especially in our structures. So this is of great interest to me to improve the overall strength of components eventually by reinforcing using additive manufacturing. Another is using ultra low density foams for sandwich composites. So far we use PVC foams, but a new system which is fly ash cyanosphere polymer foams are very lightweight, and they are just byproducts of thermal plants. So it's sustainable, and also they have added advantages of being very low density, and also they have low thermal conductivity and lower water absorption that can be used in applications where high moisture absorption is a problem, like naval hull structures, and in the presence of low temperatures, so the low conductivity helps. So this is a very recent work that I would undertake eventually. And just an offshoot of what I've been working on in the cryogenic application so far, our goal is to minimize the weight to wrap around a metallic liner. But we are interested in completely removing the metallic liner and using these composites solely as cryogenic tanks, for which we need to hybridize the material system to further account for any permeability that could occur in these extreme conditions, because they're carrying liquid fuels. So this is something that it's an ongoing future work as well. And all the work that I presented today was conducted at UTEP, and I would like to thank all my students who have helped me conduct these various legs of research. And I would like to acknowledge my funding agencies, as well as the Department of Mechanical Engineering at UTEP, and also my several collaborators within the university, as well as outside at Oak Ridge National Lab and TAMU and the Naval Surface Warfare Center, and AFRL as well. So with that, thanks for your attention, and I can take questions.